to revise what we have been doing so far, we have been discussing the effect of alloying elements, and especially of late we have been discussing the compound structures which form. So, to revise, element added can either become segregated, it can form a solid solution which can be an interstitial or a substitutional solid solution, it can be an ordered or in disordered form, and it can form an compound or an intermediate structure. Then we went on to see the kind of intermediate structures which can form, and we were discussing that we could have various kind of intermediate compounds, and we had specially discussed the differences between traditional compounds and the compounds which form in intermetallic phases, and we were discussing valency compounds, interstitial phases, electron compounds, and we were taking up the size factor compounds. We had also said this is a small subset of all the possibilities, but nevertheless this is a very illustrative subset. So, we had already taken up the size factor compounds, and we had discussed the Lavey's phases. So, let us now progress to the Frank-Gasper phases, and Frank-Gasper phases typically have somewhat complicated structures. The coordination number in these phases can be 12, 14, 15 or 16. To illustrate what are these Frank-Gasper phases, we will take up one example, and especially we will take up the example of Al12W, which has a coordination number 12. That means, if you look at any tungsten atom, for instance the tungsten atoms are located in the corners here. So, let me highlight the tungsten atoms. So, these are my tungsten atoms, and as you can see this is a body centered cubic lattice. Therefore, in my space group I have the first symbol as I, which tells me that it is a body centered cubic lattice. So, around each tungsten atom there are 12 aluminum atoms, and as we shall see they form an icosahedron around the tungsten atom. This is actually a very interesting example, though a complex example, but very nevertheless a very interesting example. If I try to calculate the number of atoms in the unit cell, I see that tungsten is located at the vertices contributing 1, and there is one more tungsten atom in the body center. Therefore, I have a total of 2 tungsten atoms in the unit cell. If you count the copper atoms, at the face centers there are 12 copper atoms, and inside the cell there are 12 copper atoms, making a total of 24 copper atoms in the unit cell. So, if I write down the formula for the unit cell, it will become Al24W2, which I reduce to Al12W. So, I have my formula Al12W, and if the total formula for the unit cell is Al24W2. Now, what is the lattice? We have already seen the lattice is a BCC lattice, and the motif now is 12 tungsten atoms and 12 aluminum atoms and 2 tungsten atoms, which is consistent with the stoichiometry of the unit cell or stoichiometry of the compound. Now, the Pearson symbol tells me that the structure is Ci26. That means that there are 26 atoms in the unit cell, and we have seen that these 26, 24 are aluminum and 2 are tungsten, okay, and this is a body centered cubic lattice. Now, if you look at other structures which form other kind of compounds which have the similar kind of structure, you have Al12Mn and Al12Mo, which also have a similar kind of structure. Looking at the lattice parameter, it is clear that it is a large unit cell, it is 7.58 angstroms, and this is therefore a somewhat of a complicated structure. So, how do I go about understanding this structure? Here you see the, this has to be a 001 view, not the 0001, it is a 001 view. You can see that, you can clearly see the kind of symmetry it is present, which is a two-fold symmetry along the 001 direction. Now, let us try to understand the coordination polyhedron in this structure. So, I was telling you that if I look at any tungsten atom, for instance the one located at the body center here, then I can see that there is an icosahedron of aluminum atoms around this central tungsten atom. Now, clearly icosahedral symmetry is not consistent with space filling. That means the local icosahedral symmetry is destroyed on long range packing. That means locally this structure has icosahedral symmetry, but in the long range, since icosahedral symmetry is not consistent with crystalline packing, therefore, I clearly see that the local icosahedral symmetry is broken. So, what is the symmetry, icosahedral symmetry I am talking about? This is actually an M3 bar 5 bar symmetry, which I write down here. So, this icosahedral symmetry I am talking about is an M3 bar 5 bar kind of symmetry, and this symmetry is broken in the long range ordering of the atoms in this alloy. An important point about this compound is that it is closely related to the quasicrystals. Okay. So, many of the quasicrystals actually have some sort of a local coordination which looks like this, but this local icosahedral symmetry pervades in the long range in quasicrystals, which is absent in this particular crystal structure, the Frank Gasper phase. But it is clear that this structure is closely related to the structure of quasicrystals, and often many of these structures are called rational approximants. So, you can see that each one of these tungsten atoms, the figure on the right hand side, you can see that each one of the tungsten atoms has an icosahedron around it, as you can see in this figure on the right hand side above, and the figure on the right hand side below shows that all the icosahedra are drawn around each one of the tungsten atoms. So, you can see that clearly that the two-fold of the icosahedron is facing the 001 direction of the cubic axis. That means along the basic directions, all along it is a two-fold direction, and the three-fold is spaced along the three-fold, so that the three-fold direction is maintained, and therefore, this is a cubic crystal. So, there are more views to understand this somewhat complicated structure. So, this is my view along the 100 direction, which shows my two-fold direction of the icosahedron coinciding with this 100 direction, which is my figure on the right. So, this is my figure on the right. You can see that this is my two-fold direction of the icosahedron, which is now coinciding with my 001 direction of the cube, or the 100 direction of the cube. Now, I also mentioned that if I am looking along the 111 direction of the cube, that 111 direction actually coincides with the three-fold direction, or the 3-bar axis of the icosahedron. So, that is what is clearly seen here. This is my now my three-fold direction, and it clearly coincides with the three-fold direction of the cube. And since the three-fold axis is maintained, is retained, I call this a cubic crystal. Okay. Now, there is also a view which is along the 110 direction of the cube, and you can use all these views to understand the somewhat complicated structure. So, if I look at the raw structure here, this might be very difficult to understand with 26 atoms in the unit cell, but once I identify my coordination polyhedra, I try to identify the symmetries of the coordination polyhedra and try to see how the coordination polyhedra are oriented with respect to the cubic axis, and therefore, how some of the symmetries are broken, some of the symmetries are retained, then the understanding of this crystal structure becomes somewhat accessible and somewhat easy. So, and again, as I pointed out, even though this is a BCC lattice, it has got 26 atoms in the unit cell of two types, aluminum and tungsten. And this, as I pointed out before, can also be understood from the Wyckoff positions they occupy. So, the Wyckoff position is 24G, meaning there are 24 aluminum atoms, and this Wyckoff number is 2, which means there are 2 tungsten atoms in the unit cell. So, we have seen that there are variety of intermediate compounds. They can range in complexity, as you see in the simple ordered structures like the copper zinc to really complex structures, and one of these was this Al12W structure, but there can be even more complicated structures, and often the number of atoms in the unit cell could go even up to 1000 or more. So, but when we want to understand these structures, often there are mechanisms or methods available to simplify the structures and to understand them. So, before we had considered the question of positional order, and we had mentioned in that context that often we define crystals either with respect to complete order, that means complete positional and orientational order, or often we define a crystal based only on positional order or only on orientational order. So, this is one example I am giving here to exemplify the point that there could be orientational order and there could be orientational disorder also in crystals. We will take up one more example later when we discuss fullerenes in the context of covalent crystals and covalent molecules, but here we take up this example wherein you can clearly see that you got chlorine ions at the corners of the cube, and there is a nitrogen at the center of the cube, and there are hydrogen which form a tetrahedron around the nitrogen atom. Now, this tetrahedron has been shown on the right hand side for clarity of viewing. Now, this kind of a structure can show orientational order and orientational disorder. So, how do I understand this orientational order and disorder? Now, in a single unit cell, for instance, the tetrahedron could be oriented such that this is my preferred orientation. That means the three-fold of the tetrahedron, this atom is located along this side of the body diagonal. It could also happen, now this edge is not along this edge, but along the other edge. That means there are two available orientations for the NH4 complex. It could so happen in a single structure that unit cell to unit cell, this NH4 complex could be oriented randomly. That means in one unit cell it could be in this orientation 1, suppose I call this orientation 1 and I call this orientation 2, then it could be the orientation could change from unit cell to unit cell. In other words, now this would be an orientationally disordered structure. The orientationally ordered version of the structure would be a structure in which you would find that every unit cell has identical orientation. That means all the NH4 ions are oriented identically from unit cell to unit cell. That would be an orientationally ordered structure. So, I could have this phase transition wherein I have typically, for instance, so let me go to the board and write it down. So, I have a high temperature structure and a low temperature structure. And could have a low temperature structure which is and the important point to be noted is that in a single crystal or in a single material, for instance, you could have regions wherein the orientational order is of type 1 in certain region. So, this I call it OR1, and there could be a neighboring region wherein you would have a domain wherein the orientational order could be different. So, you could have OR2, that means orientational order 2 in a neighboring region. Therefore, you have a boundary between these two regions which are differently orientationally ordered. So, this is clearly an example of an order disorder transformation, but this is not based on positional order, but is based on orientational order. So, this is an important point to be noted, and as I said, we will take up one more example later on, but for now this is the interesting and nice example, which is an example unlike the case where we saw the copper zinc system or the ordered intermetallics, wherein we were discussing the order with respect to positional order. So, this is clearly not that case, but this is a case of orientational order. Okay. Of course, even in these systems there could be some amount of position in many of these systems, not particularly this example, but there could also be additionally issue of positional disorder also. But since this motif in question does not have spherical symmetry, there is a possibility of orienting it in more than one way, and therefore, I have the issue of orientational order. So, this is just one example to illustrate the concept of orientational order and orientational disorder. So, now let us go back and ask some of the fundamental questions which we have of course taken up in detail to answer, but nevertheless these are illustrative examples to check our fundamentals regarding crystal structures. So, the first question we ask ourselves, do elements have simple crystal structures? The answer is they need not, and we already considered many examples to illustrate the point. For instance, you could have an element which is a simple cubic structure. That means there is just one atom per unit cell, right. In the conventional representation, polonium for instance is the only element which crystallizes in simple cubic structure, and you can see that there is just one atom in the unit cell. You could have a BCC, for instance iron, which has 2 atoms in the unit cell. You could have an example of copper, FCC, which has 4 atoms in the unit cell. You could have diamond cubic, which has 8 atoms in the unit cell, or you could have elements like beta manganese, because beta representing the kind of phase it is, there are 20 atoms in the unit cell, or you could have the alpha manganese, that means the alpha manganese and beta manganese are 2 allotropic forms of manganese. So, this is also illustrating the concept of allotropy, wherein now, and one common example of allotropy we have seen before is the existence of iron in both FCC and BCC forms, but here you see that you could have alpha manganese with 58 atoms in the unit cell. So, clearly just because you are talking about pure elements, it does not mean that the crystal structure they crystallize in need to be simple. They could get very complicated, and you can see, or they could of course be simple, but it depends on the individual element I am talking about, and there is no general rule regarding how simple or how complicated a particular element has to be. Let us try to understand, since we mentioned that this alpha manganese has 58 atoms in the unit cell, maybe later on we can take up this example. Now, the second question we are asking ourselves is that do BCC crystals, of course we could ask the same question with respect to FCC, we could ask the same question with respect to simple cubic, but here specifically we ask the question with respect to BCC crystals. Do BCC crystals have only 2 atoms per unit cell? For instance, previously I had seen the iron atom in this example had 2 atoms in the unit cell clearly. So the question we are asking, do BCC crystals have 2 atoms per unit cell? Again the answer is need not. That means if you have a simple example like iron, then you have 2 atoms in the unit cell, but BCC is a lattice and you could decorate this lattice with more and more complicated, more and more numerous kinds of atoms, and therefore you could land up with larger unit cells or more complicated structures. So for instance, there is a structure known as gamma brass, which is a copper zinc alloy, and here you have 52 atoms in the unit cell. And we will try to understand the structure in the next slide, but for now we will note that there could be 52 atoms in the unit cell. And we already seen the example of alpha manganese, which is also a body centered cubic structure, which has 58 atoms in the unit cell, and it is a body centered cubic lattice, which is. So therefore, just because a crystal is called simple cubic or a primitive cubic, it does not mean that it has to have only 1 atom in the unit cell. When there are clear cut examples of, in the case of BCC shown to you in front, that there could be, for instance, 2 or 52 or 58 or even more number of atoms in the unit cell. And in this case, of course, these 2 are elements, the iron and alpha manganese, but the copper zinc is an alloy, and this is an ordered alloy with specific crystal structure. So let me try to understand this gamma brass, because this happens to be a very interesting kind of crystal structure, and we have here at least just one slide to explain what is this gamma brass structure. Often this gamma brass structure is visualized as a 3 by 3 by 3 unit cell starting with a simple BCC kind of a or a kind of a structure. But the structure is much more complicated than that, because after making this 3 by 3 by 3 unit cell, actually you take out all the atoms from the vertices. That means all the 8 vertices are empty, and since this is BCC, that means the vertex is connected to the body center position by a body centering translation. So the body centering position should also be an empty position. Since this is vacant, this corner is vacant, as you can see here, the vertices all are vacant. So clearly the body center also, which I maybe have to draw here, the body center also has to be vacant. So all my vertices and body center are vacant, there are no atoms there. This gamma brass has been, the structure of gamma brass has been understood in very many ways, and all I am giving here is a few views. For instance, the 100 view shows how the atoms are arranged in this unit cell, and you can clearly see the 4-fold symmetry. And similarly, you can see the space filling model of this structure, wherein this copper and zinc atoms are put together to form a rather complicated unit cell. So clearly, just because I mention term simple cubic or body centered cubic, I should not be confused by that it has to be a monoatomic decoration. In fact, it could be a multi-atom decoration, or it could be a decoration with more than one kind of atoms in many numbers. So finally, we can land up with a rather complicated unit cell with a large number of atoms and or ions in the unit cell. Okay. So the next question, on the other hand, the other extreme kind of question I can ask, the first question we had asked was with respect to an element. How can an element form, what kind of structures can an element form? So the other extreme of the question is that, suppose I have an alloy with many elements. So the question I am asking, does it imply that an alloy with many elements needs to have a complex crystal structure? So this is the other extreme of the question, and the answer again is need not. Just because you have a pure element, single element, you cannot assume the crystal structure has to be simple. Similarly, if you have many elements, again you cannot assume the crystal structure has to be complex. Yes, it could be complex, or it could turn out to be very simple, and there are these examples which I am listing here, couple of examples. The details of these examples are not important, but you can see that this alloy, for instance, consists of many 1, 2, 3, 4, 5, 6 elements, and for instance this contains aluminum, cobalt, chromium, copper, nickel and iron. Of course, this subscript which I have missed out are 1, and the copper is present in half that amount, and you can see that both these alloys actually form, and of course the exact percentages are given here, the atomic percentages are listed here for these elements, and you can see that copper is present in half the amount as that as aluminum. The crystal structure, these combination, this alloy crystallization happens to be BCC or FCC, as you know, which are very simple kind of crystal structures. Of course, it cannot be an ordered structure, it has to be a disordered BCC or a disordered FCC into which these many elements crystallize into. Of course, this automatically implies that I am talking now about a probabilistic kind of a definition of the crystal, but nevertheless the crystal structure is very simple in spite of the fact that I have added so many elements. So I have to be very little wary when I am using terminology like FCC, VCC. I have to understand, like we already seen with very many examples, that when I am just because I am using a term FCC crystal, I have to ask this question: is it a monatomic decoration? Or suppose even in the case of the HCP, as Ravi had asked before, if I am talking about a HCP crystal, I have to ask, does it have an ideal Seebeck ratio before I can conclude that it is a closed packed crystal with 74% packing fraction. If, as you can see, if the ideal Seebeck ratio is not ideal, then I am not going to have a 74% packing fraction. So I should not conclude any details before asking about the details of the crystal structure and the elements which go on to form these crystal structures. So with this we conclude the topic on metals and alloys, and we will take up the topic on ionic and covalent materials. So with regard to the Frank-Gasper phase, I have two corrections to errata to point which I need to point out to you. One is that the direction 001 which I pointed out, and also the motif is 12 aluminum and 1 tungsten, not 2 tungsten. So this is to be 1 tungsten. So kindly note these two errors in the slides. The next topic we take up is the topic of ionic and covalent solids, and before that let us revise the broad picture which we started off with. We had already seen that crystalline solids we can identify molecular and non-molecular crystals. So there are two types of crystals, the molecular crystals and the non-molecular crystals. Though most of the examples we are giving are actually non-molecular crystals, but we will take up perhaps one example to illustrate the concept of molecular crystals later on in the set of lectures. Another thing which we had pointed out, though we often talk about non-molecular crystals of the type like covalent crystals or ionic crystals or metallic crystals, we have to understand that more often than not the bonding character is exactly it is not purely covalent or not purely ionic, and there is a mixed character to the bonding, and this mixed character obviously influences the kind of structures which form, and needless to say the kind of properties those structures have. So these are some of the points we need to keep in mind before we try to understand what are the principles which go on to form the ionic solids and how do we understand covalent solids. So let us start with ionic solids. In ionic solids, the motif consists of ions positioned in a lattice. So these are our usual lattices which we have been dealing with so far, and as before, to reiterate, the bonding may not be purely ionic, that means it can have a mixed character. The important thing about that, the rules we will evolve for ionic crystals may be violated when the bonding character is not purely ionic. That means whatever rules or whatever concepts we evolve to understand the formation of certain ionic crystals may be violated when the bonding character is not purely ionic. As we know already that the ionic bonds are a result of unequal sharing of electrons, that means leading to a negative charge on one of these species which we call an anion, and to a positive charge in another species which we call the cation. That means anions are negatively charged species and cations are the positively charged species, and this is coming from unequal sharing of electrons. Suppose I am talking about a covalent bond, then if there is unequal sharing in the covalent bond, then we know that it is called a polar covalent bond, and therefore it is not purely a covalent bond. We have another thing which we might have noted is that ionic bonds are non-directional, and in this sense they are similar to the metallic bond which are also non-directional, while covalent bonds have strong directionality. If when you are talking about the anion and cation and about the relative size of the anion and the cation, typically the cation is smaller than the anion. So this is something which has to be noted. There are of course exceptions, like for instance in rubidium fluoride, the rubidium ion is larger than the fluorine ion, but these are exceptions rather than the rule. There are rules elucidated by Professor Linus Pauling, the famous Nobel laureate, with regard to the formation of ionic solids, and we will try to understand the essence of these rules. We will not state these rules one by one in the way they are usually stated, but we will try to derive the essence of these rules and try to understand some of the basic crystal structures which are consistent with Pauling's rules. Now whenever I need to understand the formation of an ionic crystal, I first try to understand the local coordination, that how I can understand the formation of a local coordination which involves an ion and certain ions around it. Then I worry about the long range arrangement of these ions, which gives me the crystal. So, I always start with the local arrangement and then I go on to the long range arrangement, which would give me a crystal. So, this is my sequence. So, before I take up these Pauling's rules or the rules of formation of ionic solids, and also it's good idea to get a feel for the sizes of the various ions, typical ions, which go on to form some of the common crystal structures. For instance, one of the typical structures we will be dealing with will be sodium chloride, and here on the right hand side I have my right hand bottom corner, I have the chlorine atom and the chlorine ion, okay, and the sodium atom and the sodium ion are correspondingly given on the left hand side of the figure. So, you can see that my sodium ion is much smaller, the sodium plus ion is much smaller than the sodium atom, right, but the chlorine ion is bigger than the chlorine atom. So, once it acquires an electron, it grows in size, and typically the size could be almost twice or even more. Like you can see, if you compare the C4 plus ion, it is much smaller than the carbon atom. So, the size could be many factors or at least a factor of 2 or somewhere close to that. So, this relative sizing is very important for me when I am forming an compound between an anion and a cation, that the cation is usually smaller. Suppose I am talking about a sodium cation in comparison to the chlorine anion, then you can see that the sodium cation is much smaller than the sodium anion. So, similarly, you could talk about a lithium fluoride, for instance, and you can see the lithium cation is of course smaller than the lithium atom itself. The fluorine ion is bigger than the fluorine atom, and the lithium fluoride, you can see that the cation is much smaller than the anion, right. So, this is something which is the trend we would like to maintain, and some of these relative sizes are important to keep in the mind when we are talking about the formation of ionic solids. And as you can see, if you go down the period, the sizes of the atoms increase. So, let me go down a period. So, suppose I am going down the period here, I can see that the sizes of the ions are atoms are increasing, corresponding to the size of the ions are also increasing, which is true for the first period or the second period, where you can see beryllium is smaller than magnesium, which is smaller than calcium, which is smaller than strontium, which is smaller than barium, and similarly you can see the corresponding ions also increase in size. Again, if I look at my periods, you can see that on an average the ions on the right hand side are larger than the ions on the left hand side. So, this of course on an average, and individually there could be slight differences. So, summarize this slide, though I need to know individual ions and their relative sizes with respect to their atoms. The thing I primarily worry about when I am talking about two ions forming an ionic crystal is the relative sizes of the anion and the cation, and this will become clear when I try to elucidate the rules which govern the formation of the ionic crystals. So, as I pointed out, when I am talking about ionic crystals, I first worry about the local coordination, and then I take up the long range arrangement, which gives me a crystal. So, what are the rules for the local configuration or the local stable configuration? In this, of course, the starting assumption, as you can see, any of the starting assumptions are often violated, but we will keep these assumptions in mind when we are deriving these rules, is that the anion and the cation are assumed to be hard spheres and touch each other. This is very similar to our assumptions we made when we talked about the metallic solids, especially the close packed structures. We have to note, of course, that the anions generally do not touch each other, but may get close, because why can't ions of the same type touch each other? Obviously, they are of the same charge, and therefore, they will be a repulsive force, and this will cost energy to my system. As many anions as possible surround the cation for maximum reduction in electrostatic energy. That means, if I have a central cation, then I would like to put as many anions around it to shield the charge of the cation, which is now the smaller species. The cation is a smaller species, and this is the rule I will follow. Now, when I had used the term okay, so let me go down to some of these rules which are for the factors governing for the long range arrangement, but we have to remember that these rules we will take up later, but I have just listed them here for completeness. And there is just one point I would like to make regarding what I call the close packing in these crystals. I have to remember that ionic crystals are not close packed in the senses of CCP or HCP crystal. So, this point has been, what do you mean close packing is does not mean here the closest packing, which would lead to a packing fraction of 0.74. This is not what I mean in this case. I just mean close packing consistent with these ionic solids. So, let me summarize the rules for stable configuration, local configuration. We assume that the anion and cation are hard spheres. The anions typically do not touch each other, but somewhat can get close, and the cation would like to have a large coordination number around it of anions. This is what I have listed before. So, there is a way of listing the rules for local stable configuration. The first thing is that there should be no rattling. Suppose I have void form between my anions, then the cation should not be so small that it starts to rattle inside the void. So, let me draw a picture on the board to illustrate the point I am trying to say. Suppose I am talking about triangular coordination of ions. No, sorry, these are not coming out to be of the same size, but let me try to redraw them. So, I have 3 spheres here, and suppose these are anions which are negatively charged, and I want to put a cation somewhere inside this void which is forming this. Now, the cation cannot be so small that it rattles inside the void. So, that means it cannot be like this. If it is so small, then it will rattle. And this is not a favorable situation. The point number 2 I need to note is that the cation should be larger than the void, and this is obvious because suppose I have a cation of the correct size. So, let me use the same figure to draw a cation of the same size. So, now if I have a cation of the same size, so let me just go to the slide again just so that people they show you the cation of the same size. So, second point is that cation size should be larger than that of the void. So, this point has to be noted, and that is what I am illustrating on the board now. Suppose I have a cation of the correct size, that means it just fits into the void. This is also not a favorable situation, because if it is just of the correct size, then this anion would be touching another anion, right, which is again not a electrostatically, it will cause electrostatic energy and not a favorable situation. So, what I would like is that my central cation is larger than the void, so that my anions get separated out. So, my anions now are separated out, they do not touch each other. So, this is the picture I want to have. Now, the rule that the cation should be larger than the void sort of tells you the lower limit for the void size. Now, consistent with this, I also need to choose the largest coordination number possible. That means, I have maximum screening of the charge. That means, my cation is now surrounded by as many anions as possible, which is consistent with this void rule. So, let us consider now the radius ratios. In other words, let me find out what are my void sizes and what kind of coordination numbers those void sizes give. So, obviously, the radius ratio of relevance is the radius of the anion to the radius of the cation. Okay. Now, this will determine my coordination number or legacy, and this will also determine my local packing. Now, I will first state all these things, and I will just take up one example to show the calculation, because some of these calculations we have performed before in the context of the void sizes in FCC crystals, for instance. Okay. Now, if my radius ratio happens to be in the range of 0 to 0.155, then the configuration will be a linear configuration and the legacy will be 2. Suppose my radius ratios are in the range of 0.155 to 0.225, then I would have a triangular configuration like the one I just showed on the board, and the legacy would be 3. That means, around each cation there will be 3 anions. If my radius ratio on the other hand happens to be between 0.225 and 0.414, and you would remember these two numbers from our calculation of void sizes in FCC. So, we had noted that the octahedral void is a larger void, when the radius ratio of the atom sitting in the void to the radius ratio of the parent atom itself was 0.414, and the tetrahedral void had a radius ratio of 0.225. Now, if the radius ratio happens to be of course, for this range of anion sizes you will get tetrahedral coordination or tetrahedral configuration, and the legacy would be 4. That means there will be tetrahedron around the central cation. If the radius ratios are in the range of 0.414 to 0.732, then you would get an octahedral configuration, which means there will be 6 atoms or 6 ions of anions around the central cation. Again, please remember, we had mentioned even this term, this aspect before. Just because the word octa appears, it is not an 8 coordination, but is actually a 6 coordination. If the radius ratio happens to be 0.732 to 1, then the configuration would be cubic and the coordination number would be 8. And for instance, we will take up an example of cesium chloride wherein this is found. Okay. Now, which has got a specific Rc by R cation by R anion as 0.91. Now, if Rc by Ra is equal to 1, that means the cation is as large as the anion, then you would find our familiar FCC or HCP kind of configuration, which is a coordination number of 12. Now, there are of course these are simplified versions of the whole picture, wherein there could be many ionic crystals wherein the picture is a little more complicated. So, let us of course keep the picture simple in this elementary course, but we need to note a few points. In the above, only regular coordination polyhedra have been considered. That means, you have not considered irregular coordination polyhedra, and in some solids irregular coordination polyhedra are also found. So, this is something to be noted. And if you find irregular coordination polyhedra, as we saw in the case of the distorted octahedral and distorted tetrahedral void in BCC structure, that all there is a possibility that all the anions around a central cation may not be at equal distance. So, this is something which we need to note. So, in other words, all anions are not equidistant from the cation if you have an irregular coordination polyhedron. So, when I have a irregular coordination polyhedron, then some of the ions may be closer, some of the anions may be closer to the central cation as compared to some of the other anions which are farther away, and therefore, their interactions could have different strengths. So, this is something which is possible, but we will not take up this aspect in detail during this course. So, let us look at this coordination polyhedron and polyhedra and try to understand how they form and how they look. So, the linear coordination of course simplest to understand, and this would be stabilized for a Rc by Ra which is between 0 and 1.155. The triangular coordination, which is what we consider on the board, would be stabilized for an R cation by R anion ratio in the range of 0.155 to 0.225. Now, whenever I show a range, the lower limit is decided by the current coordination, that means whatever the coordination sphere you are showing. The upper limited is decided by the next possible coordination. That means the number 0.225 is not derived from the geometry which is the triangular geometry, but is derived from the next higher coordination, which is tetrahedral coordination, which is a 4 coordination. So, you have the 2 coordination, the 3 coordination, the 4 coordination, and the minimum possible size is 0.155 for triangular coordination, and the maximum possible is 0.225. In other words, if I have a larger radius ratio of between the cation and an anion, then it will prefer to have a tetrahedral coordination of the central cation would like to have a tetrahedral coordination of anions around it rather than a triangular coordination. And therefore, when I want to derive the number 0.155, I will look at my triangular coordination. When I want to derive the number 0.225, I will look at my tetrahedral coordination, and which we have done before in the case of void sizes in the cubic closed pack crystal and the hexagonal closed pack crystal. For the tetrahedral coordination, which is CN4, the radius ratios have to be in the range of 0.225 to 0.414, and I am talking about a central cation which is sitting in the central position, as you can see in this figure. So, this is my central cation in the center here, and this cation has 4 anions sitting around it in the shape of a tetrahedron. Again, as before, this is the least possible size, and this least possible size is not a very stable size, because in that case the anions would all be touching each other. Suppose if I have a cation of the size 0.155 times the size of the anion, then my anions will be touching each other, which is not a favorable situation. So, these are my negatively charged species, and this is my positively charged species. Similarly, if I have a radius ratio 0.2 to 5, again my anions will be touching each other. So, this is not a favorable situation. Now, the next higher coordination number possible is CN6, wherein you find that you have a 6 coordination number, wherein the central cation, which is here shaded in orange, has 6 anions around it, and this shape which it forms is the regular octahedron as shown below. So, for size of 0.414, which is determined by this geometry, and the size 0.732 will be determined by the CN8 geometry as shown by the calculation below. So, for the CN8 geometry, for instance, suppose I have a void located at the center, then suppose x is the size of the cation, of course here, which is Rc, then 2Rx plus 2Ra is equal to the body diagonal, which is root 3a, which is root 3 into 2Ra, because now my atoms are touching along this direction. So, this is my distance to Ra, and therefore, it becomes root 3 into 2Ra. That means Rx is root 3 minus 1 Ra, with Rx by Ra becomes root 3 minus 1, which is 0.732. In other words, the lower number is decided by the current configuration, the higher number is decided by the higher coordination number. In this case, the lower number happens to be 0.732, which is decided by the cubic configuration, and that means 8 anions sitting around the central cation, and the higher number is 1, which would be decided by the radius ratio Rc by Ra equal to 1, which is nothing but our cases which we have already considered, and this happens to be the case of the cube-octahedral coordination and the twinned cube-octahedral coordination. So, these two examples we already seen, and therefore, this is just a revision for us. So, we can go from coordination number 2, 3, 4, then we have 6, 8, and 8 is in the range of Rc by Ra equal to 0.732 to 1, and finally, we have when the size of the anion is equal to the size of the cation, which is we have the coordination number 12, which means that the coordination sphere has a shape, or the coordination polyhedron has a shape of a cube-octahedron or a twinned cube-octahedron. Now, these are the rules so far we have considered are the rules for local coordination. So, let us go back and revise the rules for local coordination. We said that first, number 1, that there should be no rattling. In other words, the cation cannot be smaller than that of the size of the void which it forms. The cation's size should be larger than the size of the void, and this is something very important to note, because later on we will have to replace the terminology. Often we use the terminology that the especially in the case of interstitial alloys, we use the terminology that the interstitial atom is sitting inside the void. That is the terminology. Clearly, in the case of ionic solids, the cation does not sit inside the void. So, that is not an acceptable terminology. The center of the cation coincides with the void center. So, that is a more appropriate description of the system, or in a more liberal sense, the cation sits in the position of the void, not inside the void. So, this has to be clear. In the position, of course, I mean that sits in the position of the centroid of the void. Then we also said that the system would like to increase its coordination number to have a maximum coordination of anions around the cation. So, these are the 3 rules we sort of listed, and then we tried to chalk out the radius ratios wherein certain kind of coordinations are stable, and we saw that coordination number 2, 3, 4, 6, 8 and 12 can be stable based on the radius ratios. Next, we need to worry about the long range coordination of the or the long range arrangement, which can now give me a crystal. And it is obvious that since we are talking about ionic solids and each of the species is charged, having a crystal with net charge in it would not be a stable configuration. That means I need to maintain overall electrical neutrality. So, this is the first principle, which is not very difficult to understand. In other words, if I have a local configuration wherein I land up with a net charge, for instance, suppose I have a charge of -1 on my anion and charge of +1 on my cation, then this configuration will give me a net charge of -2. And similarly, if I have a charge of -2 on minus 1 on my anion and plus 2 on the cation, then I would still end up with a net charge of minus 2. So, this minus 2 has to be offset by an overall arrangement of anions and cations, which will give me an electrically neutral system. Now, the close packing consistent with local arrangement should be realized. That means, even though I am going for close packing, whatever the local configuration I had arrived at, looking at the radius ratios, that has to be maintained. If wherever there is a possibility that the net charge on the cation is very large, it is not a small charge like 1 or 2, but it is more like 3 or 4, the cation repulsion will be very high, and then the long range arrangement, the long range order may actually try to maximize the cation distance even if close packing is not possible. So, this is something which is sometime observed, and again to reiterate, this close packing word in this context does not mean the closest packing which we typically deal with when you are talking about cubic close packed or hexagonal close packed crystals. So, let us try to take up some examples to understand the formation of these ionic crystals. Now, we have noted that when the RC by RA ratio is in the range of 0.414 to 0.732, then you would have an octahedral coordination, and the crystal structure would be an FCC or HCP packing of anions. Okay. Now, let us take the example of sodium chloride. Now, in sodium chloride, the radius of the sodium ion to the radius of the chlorine ion is 0.97 angstroms to 1.81 angstroms, which is 0.54. Clearly, 0.54 lies in the range of 0.414 to 0.732, which is in the correct range for octahedral coordination. Now, in this case, of course, in this particular example, all the octahedral void positions are occupied, but in general you could note that some of the octahedral void positions only may be occupied in some different structures, but here in this particular case all octahedral void positions are occupied. In other words, in all the void positions formed by these anions, the chlorine anions, you would find sodium cation sitting. Now, we already seen the structure and analyzed it in detail in terms of its lattice, its motif. So, we do not have to understand it for the only thing we need to understand it now in terms of the packing of the anions and cations and the charge neutrality. So, since this unit cell already we know has 4 sodium ions and 4 chlorine ions, therefore, the charge neutrality is maintained, because the charge on sodium is 1, the charge on chlorine is 1, that means there is 4 minus 4 plus in the unit cell, which means the crystal, the unit cell, which also means that the crystal is electrically neutral. So, this part is taken care of. Okay. Now, how do I understand the octahedral coordination in this, looking at the crystal structure? That is obvious, which we have already done before, but just to revise the concept, that if I take any anion, now this is my cation in the center, then this cation is surrounded by this anion here, 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 this anion here. So, it has an coordination number 6, which is what I call octahedral coordination of anions. I can similarly pick up any cation. For instance, even if I pick up this, you will find 1 is above and 1 is below, and 1 is to the left, 1 is to the right, and I will find that totally there are 6 anions around any cation, giving me the coordination number 6. Now, in this case, of course, the lattice is FCC, and the motif is, as you had seen before, is 1 anion plus 1 cation, which is now my motif. We had also seen how to understand this structure in terms of 2 interpenetrating FCC subcrystals, so or FCC sublattices, which are occupied selectively, or 2 subcrystals, one subcrystal having sodium ions and one subcrystal having chlorine ions. So, let us have a view of the same crystal in terms of space filling. So, this is a space filling model of the same, and you can clearly see from the space filling model now that the sodium ion is obviously much bigger than the void size. That means that now my chlorine anions are not touching each other. There is no physical touching between the chlorine anions, or even in this picture, for instance, this is my chlorine anion and this is not touching my other chlorine anion. So, there is no physical touching. So, my sodium ion is actually much bigger than the void, does not sit within the void, and this is a necessary condition for me to have a lower energy. And this crystal, as we have noted before, can equivalently be described either by putting the chlorine ion at the origin or the sodium ion at the origin, and these are therefore 2 equivalent pictures of the sodium chloride crystal. Now, in the sodium chloride crystal, it is not a very relevant question to ask what is there something known as a sodium chloride molecule, because in ionic solids this is just an array of sodium and chlorine ions. So, there is the concept of a molecule does not arise in these systems. In other words, the sodium ion is equi-spaced between, that means this sodium chlorine bond or this sodium chlorine distance is exactly same as this sodium chlorine distance is located in between the two, or for instance this sodium chlorine distance is also exactly the same. So, there is no molecule of sodium chloride, it is just an array of ions placed in a regular lattice, and therefore, this is my sodium chloride crystal. Now, let us take another example, and this is an example of cesium chloride, and we had noted before that suppose I have my radius ratio in the region of 0.73 to 1, then I would have an 8-fold or cubic coordination. In this case, it is observed that the crystal structure will be simple cubic with cations occupying the body centered position. So, to take up the specific example of cesium chloride, CaCl, the radius of the cesium ion to the radius of the chlorine ion is 1.67 angstrom by 1.81 angstrom, which is 0.91. So, 0.91 lies in the radius ratio regime of 0.732 to 1, which means I will have a cubic coordination and the crystal structure will be simple cubic. So, the crystal structure is simple cubic and my chlorine ions would occupy all the corners and my cesium ion would occupy the body center. Again, in this case you note that we are already approaching a radius ratio which is very close to 1, therefore, my cesium ion is almost as big as my chlorine ion. We already know how to understand this crystal structure in terms of two interpenetrating simple cubic lattices or simple cubic crystals. That means that I can have my origin of one of the sublattice at 0, 0, 0 and the origin of the other sublattice at half, half, half. One sublattice is preferentially occupied by chlorine ions, the other sublattice is occupied by cesium ions. So, to revise this slide, I have my radius ratios of cesium ion to chlorine anion as 0.91, which means that I am the correct radius ratio for an 8-fold coordination, and 8-fold coordination would imply that in the long range I am going to get a cubic arrangement which happens to be a simple cubic crystal. As I pointed out in the beginning of the set of lectures, that the bonding may or may not be purely ionic, and if the bonding is not purely ionic, then the possibilities increase, and let us consider two possibilities which will illustrate what I am saying now. So, let us take the example of silica SiO2, wherein the bonding is 50% ionic and 50% covalent. In this case, if I talk about the radius ratio, Rc by Ra turns out to be 0.29, which is in the correct region for tetrahedral coordination. So, let us look at where is 0.29 in the table which we had considered before. So, 0.29 is in the correct region for tetrahedral coordination. So, this is my tetrahedral coordination, this is what it should have. Now, it so happens that in silica the bonding, as I said, is not purely ionic, it has got some covalency to it and there is some sp3 kind of hybridization, and sp3 hybridization tells me that it needs to have a tetrahedral coordination again. Since the rules of the covalent character and the rules of ionic character are both coincident, which both tell me that there has to be tetrahedral coordination, the actual observed coordination is tetrahedral, and therefore, there is no problem, because now the additional aspect that the bond is somewhat covalent. So, this is actually a very interesting example, because now even though I have my covalent character to the bond, but still the structure happens to be ionic. I mean, what are the rules I get, the ionic character, whatever the rules they dictate, they happen to be consistent with my rules coming from the covalent character, and therefore, there is no change I need to make with respect to my understanding of the rules of the ionic bonding. Now, this is a different kind of an example, which is the example of zinc sulfide. Zinc sulfide, the two common forms is the zinc blende and the woodside structures. This is the cubic form, which is the zinc blende form, and here the bond is more covalent than ionic. If you look at the Rc by Ra ratio, which is 0.48, so let me go back to my table to see where is 0.48. So, 0.48 lies in the region of 0.414 to 0.732, which means that I need to have octahedral coordination or a coordination number 6. So, what my rules of ionic packing tell me is that the coordination number 6 is preferred. But here again you got certain covalent character to the bond, and the kind of hybridization which is observed is the sp3 hybridization, which tells me that I need to have a tetrahedral coordination, which is something like what I would have in the case of diamond. In diamond you have sp3 hybridization and you would have a tetrahedral coordination. But here the dominant factor happens to, because now what my ionic rule tells me is inconsistent with what my covalent rule tells me, there is sort of an mismatch in the kind of rules, and therefore the winner in this case happens to be the covalent character. In other words, what is actually observed is a tetrahedral coordination and not the octahedral coordination, which I would have purely understood from the rules of ionic packing. Therefore, what I actually observe is tetrahedral coordination, and the structure is shown here below, wherein I have an FCC packing of anions and the cations occupy alternate tetrahedral void positions. In other words, all the again to say, they do not sit in the void and they do not occupy all the void tetrahedral void positions, but only the alternate tetrahedral void positions. So, my lattice now is FCC, and my motif now would be one zinc and one sulfur ion. Okay. Of course, the zinc is sitting at 0 0 0 and the sulfur is sitting at quarter quarter quarter, but there are only 4 sulfur ions within the unit cell, which gives me, which they themselves form a tetrahedron. The stoichiometry for the structure is obviously maintained, because the zincs in the face centering positions and corner position together give me a contribution of 4. So, there are 4 zincs. So, the unit cell formula will become Zn4, and there will be sulfur also 4, and therefore it is Zns. So, this is my unit cell formula. So, on the right hand side you see a space filling model of the same, wherein you clearly see that out of the 8 available tetrahedral void positions, only the alternate set is occupied. Therefore, this structure obviously does not have a 4-fold axis, it has only a 2-fold axis, or equivalently looking, it has got a 4-bar axis along the 001 direction. So, this is my 001 direction, or equivalently any one of the other directions, I would have a 4-bar axis and not a 4-fold axis. Nevertheless, this is a cubic crystal, because it has got a 3-fold axis along the body diagonal now. So, my 3-fold axis, looking at pure rotational axis, now this is my 111 direction, which is now has to be a 3-fold axis, and since it has got a 3-fold axis, this is a cubic crystal. So, to revise what we have done so far, if you have pure ionic bonding, and in the most simplest cases, all I need to worry about is the first coordination shell of anions around a central cation. I have rules for local packing and I have rules for global packing, which are consistent with whatever I evolved for the local packing. The local packing is simple, that I should not have no rattling, I should have an cation which is typically larger than the void, and I would like to maximize my coordination. The fact that I have to maximize my coordination sets the upper limit for the number, the coordination shell I need to consider. That means, if suppose in the case, for instance, let me take up in the table, suppose I have an cation to anion ratio which is larger than 0.414, that means that now the cation, instead of having a tetrahedral coordination, would actually put up an octahedral coordination around it. So, since it can have a higher coordination number, it would rather not have a tetrahedral coordination, and this sets my upper limit. The lower limit is derived, as we saw, from the current configuration, which is my tetrahedral configuration. So, this we already saw. Now, the long range packing has to be consistent with the short range packing, and we had already seen that the important points was charge neutrality or electrical neutrality, and in some cases wherever there is a large charge on the cation, you would sacrifice this close packing arrangement, but rather go for maximizing the cation distance. Some of the simple compounds which are as close to ionic as possible or purely ionic as possible are sodium chloride, for instance, or cesium chloride, which obey my rules for ionic packing. But then there are systems wherein you have certain covalent character to the bonding. In other words, in those systems I find that the other rule or the other character to the bond, for instance the covalent bond, could be the dominant factor. In other words, even though in the zinc sulfide case, my rules of ionic packing told me that I need to have an octahedral coordination, what I actually land up with is actually a tetrahedral coordination for the sulfur atoms. So actually you can draw tetrahedra of sulfur around the octahedra, and this is some more views of the same zinc sulfide structure, wherein you can, some of the atoms are shown transparent for you to have a better visualization. For instance, you can see that the 4 sulfur ions clearly in this view, and there are more ions here. The 4 green ions have been shown around the sulfur ion. So this is my sulfur, and you can clearly see the 4 zinc ions are marked in green to show the tetrahedral coordination. In the picture on the right hand side, which I am marking here, I have removed all the other ions from view just to delineate the tetrahedral coordination around the central sulfur ion. So this is something we can clearly see, and in this last picture here, this is my sulfur ion at the bottom, and you can see clearly a tetrahedral coordination of zinc ions around the central sulfur ion. Now, as I pointed out, this is not this is a structure which is face centered cubic. It is so this is wrong here, so let me cross this off. This is not this is something which is wrong, so this is not true. So this is it's got a 4 bar 3m symmetry, and it does not, that means it does not have the usual 4-fold axis which many of the proper FCC crystals have. So this is of lower symmetry than the highest symmetry possible for cubic crystals. So with this we will take up covalent crystals.